So let's say something like this. If xy is equal to the square root of x minus y divided by y minus 2. We want to find, and I want to make this easier for everyone to see all the things there. That's better. So everyone can see all right. Okay, no worries. So usual domain rules apply, meaning the same sort of stuff we did in 17a for domain is still going to be valid here. Can't divide by 0. You can't take the square root of a negative. You can't take the logarithm of a negative or 0. So those are the things I'm keeping in mind when I'm thinking about what the domain of this function of x and y is. I'm going to start by saying, well, I need to exclude where the denominator is equal to 0. So I don't want y equal to 2. I usually like to say exclude y equal to 2. Some people would prefer to write y not equal to 2. Thank you. Okay. And then we have the square root. So we also need the stuff inside the root to be bigger than or equal to 0. Now, when I'm thinking about this, I'm thinking about drawing something in the xy plane. Because usually if I'm trying to describe my domain, it's going to be some portion of the xy plane. And usually I'm best at drawing things if I'm writing y as a function of x. So what I'm going to do is I'm going to solve this inequality for y if possible. Right? It's not always going to be an option, but if it is, that's usually my go-to. So I probably just add y to both sides and then say x is bigger than or equal to y, or maybe slightly easier to think of, y is less than or equal to x. I'm going to graph these two things. Well, I'm really going to graph y equal to x, and I'm going to graph y equal to 2. And when you're drawing the domain of some function of two variables, you typically want to draw anything you want to exclude. Like if you want to exclude a line, like I want to exclude the line y equals 2, I want to draw it as a dashed line. Thanks. So when I'm drawing the domain here, I'm going to say, all right, well, y can't equal 2. So here's the dashed line, y equal to 2. Can y equal x? Would that be okay? If y, as long as y wasn't 2, right? Y and x could both be 3, that'd be totally fine, right? Because the square root of 0 is something we're totally going to do. So what I'm trying to say here is we should draw the line. We should draw the line y equals x solidly, not dashed, because we want to include that boundary. Oh, okay. So there's the line y equals x. And then we have to figure out which part of this we actually want. So we just are excluding this line, right? We don't want the line y equals 2. But the line y equals x, we actually want everything, we want y to be less than or equal to x. The easiest way to figure out which side of this boundary you want is to pick a point. Pick an easy point. Pick a point that's not on the boundary. Pick something like, I don't know, 0, 1. Is that point in the domain? Meaning, or alternatively ask, does the point 0, 1 satisfy this inequality? If x is 0 and y is 1, are we good? No, we're not good, right? If x is 0 and y is 1, we have 1 less than or equal to 0. That's not right. That means this point is not in the domain, which means all of the stuff on this side is not in the domain. Can I see a symptom survey? which means all the stuff on the other side of the boundary is in the domain. So our domain is going to be all the stuff kind of below that line. Thank you. And the way I typically draw it is just kind of shading it in. So I want everything over here. I don't want this dashed line here, but I do want all of this. I want none of this. Because up here, y is bigger than x. Down here, y is less than or equal to x, which is what I wanted for this particular problem. Now, when we're talking about domain of functions of 2 variables or more variables, like you have a function of 3 variables even, talk about the domain, something like that. Usually what people are looking to get you to tell them is what the domain is kind of descriptively. Right? There are going to be, well, I don't know. Depending on how, I think professor, like I was looking at the homework assignment, the current assignment is like to do like 2 problems on Gradescope and then a few others on your own. So I don't know if you are you guys going to be using web work at all?
I don't think so.
Okay. So typically in classes past, there'd be like a web work question. It'd be like, here's the function, and here's this drop down menu of things that maybe describe the domain. Is it a line? Is it a plane without a line, et cetera, et cetera, et cetera. So since that's not really going to be, I don't know. I guess I'm not. He might actually have you draw a domain like this, or he might not. I don't actually know. Actually, actually, let's find the largest possible domain. So I wonder what he wants you to do for that first question, right? Because if I was doing it, and what I would encourage you all to do for that first question, even though it doesn't specifically say it, is to draw the domain, because that's going to be the most informative answer. We can also write some stuff. It's not going to be very interesting though. Here's how you write the domain. Prepare to not be excited. It's the set of all points x comma y such that these things are true, such that y is not equal to 2 and y is less than or equal to x. It's kind of lame because it's not telling us anything that we didn't already know. Whereas this here is a bit more descriptive. It's informative. I'm like, oh yeah, I can see the values of x and y. Sorry, I should say the points x, y that are actually in the domain of this function. A harder question to answer here, but a more interesting, well, not more interesting, an equally interesting question is, what about the range? Nine times out of 10, probably more, when you have a function of more than one variable like this, and you have a fraction, almost always get every real number in the domain. It's a pretty good bet that you're going to get everything. Sometimes you don't get 0 if the denominator can't be 0, or sorry, if the numerator can't be 0. Apologies. Like if your function was something else like 5 over x plus y, you can probably get everything except for 0 in the range, but you definitely can't get 0 because to get 0, you have to have 0 in the numerator. And that's not going to happen for 5 over x plus y. Here's how I justify to myself what the range is. I try to make it easy. I'm going to pick a specific value of y to make the denominator super easy. Like I'm going to pick y equal to 3. And then I'm going to ask myself, if y equals 3, what values can the function equal? Let's write it down. This is not by any means like a, I don't know, like, no, this is not like in the book. No one tells you to do it this way. This is just what I've come up with because it works most of the time. If I put y equal to 3, my function is now kind of weird, but it's f of x comma 3, and it's the square root of x minus 3 over 1. Actually, set the survey. X can be anything. Well, that's not entirely true, actually. X can be anything bigger than or equal to 3, right? Because we set a y value. We're kind of living over here where y is equal to, we're really like, here's y equal to 3. we're living on this line right now. Not that it really matters, but just kind of need to see, right? We picked y equal to 3. So x can be anything that is bigger than or equal to 3. But the point really is, what kind of values can they get at? Well, if x is 3, what's the function equal to? Yeah, it's 0. Yeah. And can we get negative values? Right? We can't get anything negative. If x is 4, we get the square root of 1, which is 1. If x is 6, we get the square root of 3, which is the square root of 3. But everything we're getting is positive. But we can get every positive number. Right? X can get larger and larger and larger and larger and larger. We're not going to miss anything. So if y is equal to 3, we can get every possible positive number. Actually, I should really say we can get every possible non-negative number because we can get the function equal to 0 as well. And if we pick another convenient value for y, like y equal to 1, then we get f of x comma 1 equal to the square root of x minus 1 over negative 1. Now, in the same sort of way, we can get every possible negative output because the top can be any possible positive number or 0, and we're dividing by negative 1. So to me, this is how I'm showing to myself, oh yeah, the range can literally be anything. There are other ways to achieve this, but when you have something fractional specifically like this, it's kind of just figure out how to justify to yourself what's going on. There's not really a good method that works every time for this. Also, you're not often asked to find the range of something like this, but it seemed worth mentioning. Let's look at another one. Unless you have questions. Don't hesitate to ask questions if you have questions. All right. I left my water bottle somewhere. It was not smooth. Where did I leave it? Oh, wow. I'm very curious though, because like, I really thought I walked out of my office with it. No, I don't know. Oh, well, I guess I'll just be thirsty. So let's look at the next one. Let's change it up a little bit. Sure. Let's say our function is the square root of 9 minus x squared plus the natural log of 1 minus y squared. And again, we want to find the domain, and we may or may not talk about the range. The range might be kind of screwy. The range is usually kind of screwy. Excuse me. So I have a couple issues. I have a square root and a log. I know for the stuff inside the square root, it's got to be non-negative. I know for the stuff inside the logarithm, it's got to be strictly positive. There's a couple ways to tackle this. I think I would like to say that you have probably seen enough math to kind of jump to the conclusion that if 9 minus x squared is bigger than or equal to 0, x has to be between 3 and negative 3. You could do some factoring. You could bring the x squared over to the side, square root an absolute value. But we can kind of see if x is bigger than 3, you're going to have a problem. 9 minus 4 squared is negative. If x is less than negative 3, we're going to have a problem because 9 minus negative 4 squared is also negative. And in the same sort of way, here we're going to get y having to be between negative 1 and positive 1. If y is bigger than 1, we don't satisfy the inequality. If y is less than negative 1, we don't satisfy the inequality. You could also do this with some factor, right? You could be like, oh yeah, this is 3 minus x times 3 plus x. This is 1 minus y times 1 plus y. But that's not really the point of this question. So let's graph the domain. So x has to be between 3 and negative 3, including the boundary. So I'm going to draw bold, solid vertical lines, x equals 3 and x equals negative 3. And then y between negative 1 and 1, but I don't want to include those boundaries. So y equals 1 I'm going to draw as a dashed line to indicate that it is not part of the domain. And the same thing for y equal to -1. So my domain is going to be everything in this rectangle, including this boundary here and this boundary here, but not this dash boundary here and this dash boundary here. Question: is this point where those two things meet included? I think not, right? Because if I had that point, y would be equal to 1, and y can't be equal to 1. So I can't have this point, it can't have that point, it can't have that point, it can't have that point. And I'll just mention again that the way of writing this domain is very unexciting. You're literally just saying it's the set of all points in the plane such that this is true and this is true. Oops, less than, not less than or equal to. That's it. So writing the domain in the set builder notation is what it's often called. Doesn't really say more than we've already done. We should talk about the range because the range is actually moderately interesting here. The range is going to be a little bit of work. So these are kind of separate from each other. We're going to deal with them separately. Square root of 9 minus x squared. What's the smallest that could be? That's a good question. I mean, 1 takes a lot. I'm like, water bottle. Oh, no, okay. Can I hide it in here? Oh. So, what's the smallest that can be? Everybody say something. I know you just don't want to say it. For the square root, the smallest output you can get is when x is 3 in this case, which gives us what for y, or for the function value. 0. You can say 0. It's okay to say words. I know it's been a long time in this world, but you can say stuff. The smallest this can be is 0. And that's true for any square root. Like maybe it's actually larger than that, but the smallest thing it can ever be is 0. You can't get a square root of something and get a negative value out. On the other hand, for this particular expression, what is the most large it could be? Well, to make this large, you want to make that part small, so just subtracting it off. So the largest this could be is when that's going to be 0. And we're going to get what out. Yeah, thank you. Okay, the natural log one's a little bit dicier. Not a lot dicier, but a little bit dicier. To deal with natural log, I'm going to think about what the natural log looks like. Regular good old y equals natural log of x for just a second here. Looks like this. Has an intercept at 1, 0. And typically has a range from -infinity all the way to positive. But we're limited because this here, the insides here can only be, the insides here can be pretty darn negative. We can't take the log of a negative. We are very limited in that 1 minus y squared is going to be less than or equal to 1. And, oh, sorry, what's that? Yeah, thanks. Please don't hesitate to let me know if something's off screen. It's going to happen all the time. Just say, James, can't see what we're seeing, and let me know. But we already know that this has to be greater than 0. So what's happening is for the logarithmic function, we're kind of stuck in this part right here, where our input is between 0 and 1, and our output is stuck being negative or 0. So what I'm really saying is, for us, the natural log of 1 minus y squared has to be between 1 and 0. There is no other choice. Wow. So I said that totally wrong. Moderately wrong. That's what the insights have to be. I was trying to talk about what the log is supposed to be. Right. So it is true that 1 minus y squared is between 0 and 1. The natural log of that is between the natural log of 0 and the natural log of 1. Natural log is 0. Okay, I shouldn't really write that. What I'm really saying is we're going down to minus infinity is less than the natural log of 1 minus y squared. Is less than or equal to the natural log of 1, which is 0. Sorry about that. That was a mistake. If we add these two things together, well, it's got to be less than or equal to 3 plus 0 and bigger than or equal to 0 plus negative infinity. So it looks like we could justify that our range is everything from negative infinity up to positive 3. You could totally get positive 3 by setting x equal to 0 and y equal to 0. And you could totally get anything less than that by letting x and y be different values. Question?
Do you multiply that 1 by 0? The one in the red parentheses?
Right there?
Yeah.
No. I'm taking the natural log of it. And the natural log of 1 is the power we raise e to get 1.
Which would be 0.
Which is 0. And log base anything of 1 is always going to be 0 because the base raised to the 0th power is always 1 regardless of the base. As long as it's like a normal base, not some weird thing. Well, not some disallowed thing. All right. Let's look at, what time is it? I'm trying to be judicious with the time. We can talk more about domain and range, but I feel like let's do one more. Let's look at f of x, y equal to 3 plus 2 times sine of 4x plus 2y. Is there a fraction? Is there a square root? Is there a logarithm? Great, the domain is everything. If you don't see one, so I should backtrack something. There is one other type of function that has domain issues. You're just probably never going to see it in this class. And the other type of function is an inverse trig function. So if you had a function that was inverse sine, or inverse tangent, or inverse secant, or inverse cotangent, cosecant, or cosine, those also have domain restrictions, but you almost never see those in this context, so it's not something we typically do for. So my rule of thumb is if I don't see a fraction, a square root, or a logarithm, then the domain is everything. Notably, I should point out, tangent is a fraction. Right? Tangent of x does have a domain restriction because it's really sine of x divided by cosine of x. And then you have to worry about cosine of x being 0. But that's not an issue we have here. There are no domain restrictions. Okay, so this is where you have to be careful, though. You don't get to say that the domain is negative infinity to infinity. Because it's not the real number line, it's the entire real number plane. So the domain here is the set of all points x comma y. You could really just say that, such that x and y are both real numbers. Or alternatively, it's the entire plane. If you wanted to draw it, it wouldn't be very exciting. You would draw your XY coordinate system, and then you would shade the whole thing in. How exciting. The range here is a little more interesting. We can definitely find the range of this. And here's an important fact that I imagine probably all are aware of. Sine of anything is always between what two numbers? Thank you. Specifically, in this case, sine of 4x plus 2y is definitely between -1 and 1 always. And you can get the values of 1 and -1 by making the input pi over 2. And we can definitely make the inside pi over 2 by picking something in the xy plane that will work for that. Right? I mean, we could actually make it like x could be pi over 8, y could be 0. That would make it work. So then we can quickly make this look like this. Multiply both sides by 2. So then -2 is less than or equal to 2 sine of 4x plus 2y is less than or equal to 2. And then add 3. So let's see, we have 3 minus 2, so that's 1, is less than or equal to 3 plus 2 times sine of 4x plus 2y is less than or equal to 5. So here's our range. It's everything between 1 and 5, inclusive of the endpoints. Oh, I know what I want to say. I want to say one other small example. What I should mention though, for these types of functions of more than one variable, the domain is always going to be some sort of portion of the xy plane, or if it's a function of x, y, and z, some portion of the three-dimensional space. Whereas the range is always still just going to be an interval, because we're talking about the value, the single values that we get out, right? It's not, you're not getting an output that's a pair of events, you're getting an output that's a value. So the range will still be kind of normal-ish in that it's an interval of values, whereas the domain is some set of points in 2 or 3 dimensions. I'll give you one more example. This is similar to a homework problem I saw. Actually, let me have the book literally right here. Trying not to do, where'd you go? Sorry, there was a problem I saw that looked worth mentioning. I just want to point it out to you all. Where did you go? Sorry, I was just looking at it. It seemed very important that I mentioned this one, so I don't want to just pretend it is not there. Where did it go? I had seen it. I know my brain made note of it, and now it's disappeared. I'm so disappointed. Well, here's what I thought I saw. I thought I saw a function like this. F of x comma y comma z equal to something like, although I'm going to change it a little bit, the square root of x minus the square root of y minus 2 plus the square root of z. I really feel like that was in there. Oh, there we go. Problem 11. Ooh, theirs is a little bit more complicated though. Interesting. So this function, I just want to mention, has a domain as well. And the domain is, well, it's actually not too terrible to figure out. X has to be greater than or equal to 0. Y minus 2 has to be greater than or equal to 0. And z has to be greater than or equal to 0. So we have y really greater than or equal to 2 there. We can draw this. It's kind of a pain. Ooh, we can do that too. Yeah, maybe we'll do that. So if I want to draw this in 3 dimensions, which I should because it is, x is this axis that's pointing at you, y is this axis to the right, and z is this axis pointing up. So if I want where x is bigger than or equal to 0, I want everything in the front half of space. And if I want everything where z is bigger than or equal to 0, I want everything in the top half of space. And if I want everything where y is bigger than or equal to 2, I want everything in the right half of y equal to 2. So I'm limited by, let's say that's 2 there. I have to be in this direction, because I have to be x bigger than 0. I have to be in this direction, because z has to be bigger than or equal to 0. And I have to be in this direction, because y has to be bigger than or equal to 2. So I'm there's not really a good way to draw this because you're just trying to draw like a block of space, but you're kind of limited to this octant or eighth of space where things keep going out in each of these directions. So things keep going up and forward and to the right, but not back and not that, and not to the left. Most of the time we stick to functions of two variables, but sometimes there definitely is a question 11, where they ask you about the domain. Yeah, the domain of a function like that. So for that kind of question, you're describing all the points in 3 dimensions. And so if you wanted to write this in, again, the not very exciting way, the domain here would be the set of points x, y, and z such that these 3 things are true. X is bigger than or equal to 0, and y is bigger than or equal to 2, and z is bigger than or equal to 0. And I suppose I should have been, usually when I'm drawing in 3 dimensions, I draw with dashed lines just because that's how I draw in 3 dimensions. But I suppose I should have used solid lines to include the ends of my boundary because they should be included. So that should really be more of a, whoops, that should be more of a solid. So there's our box that continues up and forward and right. Let's talk about some level curves. I know I had a good, so many pieces of information. There we go. Yeah. So when we talk about level curves, you're really just asking, what does this graph look like in the plane z equal to something? And the most common level curve we're ever going to draw is when z is equal to 0, which is also known as the trace of a function. Well, I should say one of the traces. So let's look at a couple examples here. And yeah, let's start with that. That's a good example. So let's say we have f of xy equal to x squared plus y squared minus 4. Let's do that. And we're going to talk about how we would graph this in 3 dimensions. I don't think you're going to do a whole lot of 3-dimensional graphing in this class, but there's probably like this much, so we should talk about it. Let's talk about the traces first. So the traces are just what you get in each of the 3 different planes, meaning the xy plane, the xz plane, and the yz plane. So if we're looking at 3 dimensions here, or as I often like to say, if you pretend like, I'm trying to think of a good point here. If this is your origin here, at this corner right there, the ground is the xy plane. And actually, I should really take the corner of the room. It's a little easier there. If the corner of the room over there is the origin, we're in the first octant. Here's the xy plane. Here's the yz plane. Here's the xz plane. So the xz plane is the one that's slicing out towards you. The yz plane is the one that's kind of the one that looks flat to you. And the xy plane is the one you're standing on. That's the way I'm always thinking of it. I'm always thinking about facing those planes. I can push forward towards the the yz plane. I can push to the left towards the xz plane, and I can stomp on the xy plane. And those are the planes we want to find the traces of. They help us graph them. If you're in the XY plane. You haven't gone up or down, right? You're at the ground level, essentially. If you're on the XY plane, what do we know? We know z equals 0. It's a lot like finding your x-intercept in 2 dimensions. When you find your x-intercept, what do? You set y equal to 0. When you're finding what's happening in your xy plane, what do? You set z equal to 0. You set z equal to 0, also known as the function. We're going to get x squared plus y squared minus 4 equal to 0. And when I see something like that, I'm like, oh, it's a circle. X squared plus y squared equals 4. So in the xy plane, my trace is the circle of radius 2. Okay, let's see what's happening in the other planes. Let's find the other traces. In the YZ plane, which is the one I usually draw first, because it's the one that's the most like drawing on the piece of paper, because it's the one that's kind of flat. I'm going to set x equal to 0. Right? It's just like the intercepts. Y-intercept, you set x equal to 0. X-intercept, you set y equal to 0. In the planes, to find what's happening in the YZ plane, well, if you're in the YZ flat plane, right, if you're here on the wall, if you're on the wall, you're in trouble. Okay, well, one more time. Well, maybe you shouldn't hit the wall so hard, James. Great. Okay, I fixed it. Awesome. So I won't hit the wall so hard. But if you're on the wall, gentle, nice wall, we love very much. You haven't moved out that way, and you haven't moved back that way. What I'm trying to say is your x value is 0. So if you're in the YZ plane, you figure out what's going on by setting x equal to 0. And if x is 0, I'm going to get z equal to 0 squared plus y squared minus 4. And that's a parabola opening upwards, shifted down 4. I should be more specific. This is x, y. This is y, z. And we're going to get a very similar thing in the xz plane, where we set y equal to 0 and get z equal to x squared minus 4, which literally looks the same as the other one. So the point of drawing all these is that you can kind of smush them all together to make one 3-dimensional picture. Right? What I've got going on here is a parabola opening up this way, a parabola opening up that way, and a circle in the flat plane. I would draw what's happening in the YZ plane first. So here's my parabola in the YZ plane. And then I'd draw what's happening in the XY plane. Now I'm trying to draw a circle. I'm trying to draw a circle in this flat plane that's not right. It's not like it's. You have to think about perspective, is what I'm trying to say. There's my circle in the XY plane. And then finally, I'm just going to take that point there where my circle meets the x-axis and that point there and try and draw the parabola through them. And maybe I'll draw another little circle up here. There's my paraboloid, is what that thing is called. That's kind of the technique for drawing things in 3D, if you happen to have traces that are relatively not awful. But honestly, I would remind you all that you have tools available to you. Not that one, actually. Desmos is great, but not for really graph. There's like a 3D graphing thing kind of in Desmos. It's not wonderful. But if you go to GeoGebra/3D, you can actually do some pretty decent 3D graphing. And it really, like, there was definitely a problem, I think a quarter or two ago in 17C, that it was like really hard to see the visuals, like to even understand what's happening. But when we graphed it using this, it was like, oh, we can see these, like this plane is parallel to this line. It was like super informative. So I would strongly encourage all of you, if you're having trouble seeing something, it's worth looking at it in a 3D graphing utility. Here, it's great. Z equals, what do we got? X squared plus Y squared minus 4. Oops. When you do this, make sure that when you add, you get out of the exponent there by pushing the right arrow. And it's beautiful, right? It's not there. Where'd it go? Why aren't we getting it? So sometimes things work great. Sometimes maybe not. There we go. I was like, okay. So there is our, I wonder what they're doing. So there's a lot of extra things going on here, but we can see what's happening. They look like they've drawn some interesting level curves, but you can definitely see the shape of this thing, right? It looks like a parabola that's kind of been rotated around, it's opening upwards. A couple more things about this particular shape. That's not what I wanted. Holy smokes. Why are you in the spot? I can't see. There we go. So the thing I really want to talk about was the level curves here. So what's a level curve? A level curve is just what's happening in the plane that's parallel to the XY plane for some Z value. So a level curves, first of all, we have to pick values for Z that are in the range. We can actually ask ourselves, what is the range of this function? So if we have f of xy equal to x squared plus y squared minus 4, the domain is certainly everything, all points in the plane. But our range is limited here, right? If I look at the picture, if you think about the range is how high and low this thing can go, because we typically draw the z-axis as the vertical axis. It can go up forever, but our bottom value is, what's that point there? Yeah, so our range here is definitely limited. Our range is -4 to infinity. And when you're talking about finding level curves, you're finding level curves for values of z that are in the range. So for example, we could pick, well, in fact, we've already picked z equal to 0. It wasn't very exciting. And not that it wasn't exciting. We just took our function and set it equal to 0. And then we got x squared plus y squared equal to 4. Circle of radius 2. But then we can pick other values like z equal to, I don't know, let's say, I'm going to try and pick something nice, like z equal to 1. It's not going to be nice. That's fine. X squared plus y squared minus 4 equals 1. I get x squared plus y squared equal to 5. So this one has a radius of 2. This one has a radius of the square root of 5. This is going to get tedious really fast. We can see that we're going to get circles every time, but it would be nice to kind of have a way of just knowing what the radius is going to be instead of having to do the math every time. So here's what we're going to do. We're going to say, I'm going to set z equal to just some constant c. And then if we do that, we get x squared plus y squared minus 4 equal to c. And then solving for x squared plus y squared equals 4 plus c. So that's a circle centered at the origin, and the radius is the square root of 4 plus c. So if I wanted to draw, oh, what's the word I'm looking for? Sorry. I want to draw a bunch of level curves in the same plane. Here's how I'm going to do it. So I know that for, well, really for any C value, our level curve is a circle of radius square root of 4 plus C. So when C is as small as possible, I should move this up a little bit. Right, when C equals -4, we get a lame circle of radius 0. Circle of radius 0 is kind of not really a circle. It's really just a point. We do need to label. So this is where things get a little bit just kind of annoying, maybe, is that here we have to label the level curves if we're drawing this on the XY plane. And then I would probably try and pick convenient values. So usually people try and do this in the way where you get nice roots out. So I might graph for like C equals -3 because the radius is going to be 1. And then I might do when C is equal to 0 because the radius is going to be 2. Oops, wow, that circle is not really a circle. Sorry about that.